Today we're going to explore one of the most fascinating phenomena in food science, the melting cheese texture paradox. This is a scientifically rigorous look at why cheese can melt smoothly, yet suddenly turn rubbery or separate. Here's the central question. Why does cheese sometimes melt into a smooth, creamy liquid, but other times separate into greasy oil and rubbery curds? The answer involves understanding how protein networks behave under different temperatures. Cheese contains casein proteins that form a complex three-dimensional network. This diagram shows the casein protein network in cheese. The white circles represent protein clusters, and the green lines represent the bonds connecting them. This network gives cheese its structure. Now here's where the paradox emerges. The protein network undergoes two competing transitions when heated. First, there's protein softening. As temperature increases, the protein bonds weaken and the network becomes more fluid. This leads to smooth melting. Second, there's protein aggregation. At higher temperatures, proteins can denature and form new, tighter bonds. This leads to the rubbery texture. The critical insight is that small temperature overshoots can push the system from one phase to the other. Just a few degrees can mean the difference between creamy and rubbery. Let's look at the physics. The first transition involves the glass transition temperature, denoted Tg. For most cheeses, the glass transition temperature is around 10 to 20 degrees Celsius. Below this temperature, the protein network is rigid like glass. Below Tg, cheese behaves like a glassy solid. It's hard and brittle. This is why cold cheese from the refrigerator is difficult to spread. Above Tg, the proteins gain enough thermal energy to move. The network softens, and cheese becomes pliable and can flow. Now let's talk about the actual melting range. Cheese doesn't melt at a single temperature like ice. It melts over a range. Most cheeses begin to melt significantly between 60 and 90 degrees Celsius. The exact range depends on moisture content, fat content, and the type of cheese. Cheeses with higher fat content tend to melt at lower temperatures. Fat acts as a lubricant between protein strands, allowing them to slide past each other more easily. Cheeses with lower moisture content require higher temperatures to melt. The proteins are more concentrated and need more energy to separate. Here's where things get tricky. There's a critical temperature above which proteins denature irreversibly. We call this Td, the denaturation temperature. For casein proteins in cheese, Td is typically between 70 and 90 degrees Celsius. Notice this overlaps with the melting range. This is the source of the paradox. Let me ask you a question. Why does protein denaturation cause the cheese to become rubbery? When proteins denature, they unfold and expose hydrophobic regions that were previously hidden. These regions stick together, forming new, stronger bonds. On the left is a native protein folded into its natural shape. When heated excessively, it unfolds into a denatured state, shown on the right. This unfolded protein can now form aggregates. We can model this using free energy. The system wants to minimize its Gibbs free energy, denoted G. Gibbs free energy equals enthalpy minus temperature times entropy. H is enthalpy, T is temperature in Kelvin, and S is entropy. At low temperatures, the enthalpy term dominates. Proteins maintain their folded structure because it has lower enthalpy. At high temperatures, the entropy term becomes more important. Unfolded proteins have higher entropy, so the system favors denaturation. Now let's identify the critical temperature window for perfect cheese melting. The optimal melting temperature is typically between 60 and 70 degrees Celsius. In this range, proteins soften but don't denature significantly. Below 60 degrees, the cheese doesn't melt enough. It remains too solid and won't flow smoothly. Above 70 degrees, you enter the danger zone where denaturation becomes significant. The cheese can turn rubbery or separate. Let's work through a concrete example. Consider mozzarella cheese on a pizza baking at 230 degrees Celsius. The oven is at 230 degrees Celsius, much hotter than the denaturation temperature. However, the cheese surface only reaches about 100 degrees Celsius because of evaporative cooling from moisture. Here's an interesting question. If the cheese surface reaches 100 degrees, which is above the denaturation temperature, why doesn't it always turn rubbery? The answer is that time matters just as much as temperature. Protein denaturation is a kinetic process, meaning it has a rate. The rate constant K follows the Arrhenius equation. K equals A times e to the negative EA over RT. A is the pre-exponential factor, EA is activation energy, R is the gas constant, and T is temperature. If cheese stays at 100 degrees for 10 minutes, there's significant denaturation. This is why overcooked pizza has rubbery cheese. But if the cheese only stays at 100 degrees for 2 minutes, denaturation is minimal. The cheese melts beautifully without becoming rubbery. Now let's address the oil separation phenomenon. Sometimes when cheese is overheated, it separates into oil and curds. Remember that cheese is fundamentally an emulsion. Fat globules are dispersed throughout a protein and water matrix. The orange circles represent fat globules dispersed in the protein matrix, shown by the white rectangle. This emulsion is stable when the protein network is intact. When proteins denature and aggregate tightly, they squeeze out the fat. The fat pools on the surface as oil. This phenomenon is called syneresis. It's the expulsion of liquid from a gel network due to contraction. We can understand syneresis thermodynamically. It's driven by a decrease in free energy. The total change in Gibbs free energy for the system equals the change for the protein network plus the change for the fat phase. For syneresis to occur, this must be negative. Protein aggregation is exothermic, meaning it releases energy. The change in G for the protein network is negative. Fat droplets coalescing into larger pools also decreases surface area and releases energy. This also contributes negatively to delta G. Together, these two processes drive the phase separation we observe as oil weeping from overheated cheese. Now let's discuss practical solutions. How can we prevent cheese from turning rubbery or separating? Solution 1 is to control temperature precisely. Keep cheese in the optimal range of 60 to 70 degrees Celsius. Solution 2 is to add emulsifying salts like sodium citrate. These salts chelate calcium ions in the protein network. Sodium citrate reacts with calcium ions. This weakens the protein network bonds, making the cheese more stable during melting. This is exactly how processed cheese products stay smooth. They contain emulsifying salts that prevent protein aggregation. Solution 3 is to add starch or flour. Starch absorbs water and fat, stabilizing the emulsion. Solution 4 is to choose younger cheeses with higher moisture content. These melt more smoothly because the protein network is less concentrated. Let's talk about an often overlooked factor, pH. The acidity of cheese significantly affects melting behavior. pH equals negative log of hydrogen ion concentration. Most cheeses have a pH between 5 and 6. At pH below 5.0, proteins carry more positive charge. This increases electrostatic repulsion, weakening the network. At pH around 5.2, we're near the isoelectric point of casein. Here, proteins have minimal net charge and aggregate most easily. At pH above 5.5, proteins carry negative charge. Electrostatic repulsion prevents excessive aggregation during heating. This explains why aged cheddar, which has a lower pH due to continued fermentation, is harder to melt smoothly. Let's create a quantitative phase diagram for cheese texture as a function of temperature and time. This phase diagram shows 3 regions. Green is solid cheese below melting temperature. Yellow is the optimal melted state. Red is the rubbery or separated state from overheating. Notice the boundaries between phases are not sharp. There's a gradual transition, which is why small temperature changes can have big effects. Let's calculate the activation energy for casein denaturation. This tells us how sensitive the process is to temperature. The activation energy for casein denaturation is approximately 280 kilojoules per mole. This is relatively high, meaning the process is very temperature sensitive. Let me ask, what does this activation energy value mean practically? For a reaction with this activation energy, increasing temperature by just 10 degrees roughly doubles the denaturation rate. This explains why small overshoots matter so much. Using the Arrhenius equation, the rate at 80 degrees divided by the rate at 70 degrees equals e to the EA over R times the difference in reciprocal temperatures. This gives approximately 2.1. Let's look at a real-world example. Cheese fondue. Fondue is a classic case where understanding this paradox is crucial. Traditional Swiss fondue uses Gruyere and Emmental cheeses. These are carefully chosen for their melting properties. Wine is added not just for flavor, but to lower the pH. The acidity helps keep proteins from aggregating too strongly. A small amount of cornstarch is added to stabilize the emulsion and prevent separation. Most importantly, the fondue pot temperature is carefully maintained around 65 degrees Celsius. This is right in the optimal melting zone. If the fondue gets too hot, above 75 degrees, it becomes grainy and oily as proteins denature and fat separates. Let's zoom in to the molecular level and see what's really happening during cheese melting. Casein proteins form micelles that are held together by calcium phosphate bridges. These bridges connect different protein molecules. Here we see two casein proteins connected by a calcium bridge. The orange dot is a calcium ion that links the proteins together. When heated, thermal energy weakens these calcium bridges. The proteins become more mobile and can slide past each other. However, excessive heat causes the proteins themselves to unfold. Hydrophobic regions that were buried inside become exposed. These exposed hydrophobic regions are sticky. They form new, strong hydrophobic interactions with other unfolded proteins. These new aggregates are much tighter and more irreversible than the original calcium bridges. This is the rubbery texture. Different cheese varieties behave very differently when melted. Let's compare a few. Mozzarella has high moisture content, around 50 to 60%. It melts beautifully with good stretch. Young cheddar with 35 to 40% moisture melts well. Aged cheddar is drier and more acidic, so it melts less smoothly. Parmesan has only 25 to 30% moisture. Its protein network is so concentrated that it barely melts, even at high temperatures. Halloumi has a uniquely high melting point due to its high pH and specific protein structure. It can be grilled without melting. The single best predictor of melting behavior is moisture content. More moisture means lower protein concentration and easier melting. Understanding this paradox has enormous industrial applications. Processed cheese products are engineered to avoid the paradox entirely. Emulsifying salts like sodium citrate and sodium phosphate chelate calcium ions. This prevents the formation of strong calcium bridges. By removing free calcium ions, the cheese proteins remain dispersed and can't form tight networks even at high temperatures. This means processed cheese can be heated, cooled, and reheated multiple times without developing a rubbery texture. The trade-off is that processed cheese loses the complex flavor development of natural cheese, but it gains stability. Let's talk about practical implications for cooking. How should you handle cheese to get the best results? First, always use low to medium heat. High heat is the enemy of smooth cheese melting. Second, grate cheese finely. Smaller pieces melt faster and more evenly, spending less time in the danger zone. Third, add cheese near the end of cooking. Don't subject it to prolonged heat. Fourth, toss shredded cheese with a small amount of cornstarch. This prevents clumping and stabilizes the melt. Fifth, remove from heat immediately once cheese is melted. Residual heat will complete the melting without overshooting. Let's examine one special case, the stretching property of mozzarella. Why does mozzarella stretch while cheddar doesn't? Mozzarella is a pasta filata cheese, meaning it's stretched during production. This aligns the protein strands. The mechanical stretching aligns casein proteins parallel to each other, like fibers in a rope. This shows the aligned protein structure in mozzarella. The parallel strands can slide past each other when heated, creating the stretch. When heated, these aligned fibers soften and can slide past each other, but they remain connected. This creates the characteristic stretch. Cheddar has a random isotropic protein network. When it melts, it just becomes a liquid without any directionality or stretch. Let's get into some advanced rheology. Rheology is the study of how materials flow and deform. Melted cheese is viscoelastic, meaning it has both viscous liquid-like properties and elastic solid-like properties. The shear stress tau equals viscosity, eta, times shear rate gamma dot. This describes the viscous component. The shear stress also equals shear modulus G times strain gamma. This describes the elastic component. At the optimal melting temperature, both viscous and elastic components are balanced. The cheese flows smoothly but maintains some structure. When cheese is overheated and proteins denature, the elastic modulus increases dramatically. The cheese becomes more solid-like and rubbery. Let me summarize the core of the melting cheese texture paradox. Cheese contains a complex casein protein network held together by calcium bridges and hydrophobic interactions. Heating causes two competing transitions: protein softening and flow versus protein denaturation and aggregation. The optimal melting range is 60 to 70 degrees Celsius, where softening dominates but denaturation is minimal. Small temperature overshoots of just 5 to 10 degrees can push the system into the rubbery phase, where denaturation dominates. Time exposure also matters. The longer cheese stays at elevated temperature, the more denaturation occurs. pH, moisture content, and fat content all affect the delicate balance between these competing transitions. Understanding this paradox allows us to control cheese texture through careful temperature management, choice of cheese variety, and use of stabilizers.